Hey everyone in Chemistry 40S and Chemistry 40SH country. It's Dr. Carroll here. We're looking at lecture number 1 in Unit 6, all about acids and bases. You know they have two different faces. There's a song about that. I'll try to find it somewhere. I once bought it for like $5 online from some guy who plays a banjo. If you ask some of your colleagues from first semester, there are a few of those guys who just sang the song nonstop. So today's lecture is just reminding us of the properties of acids and bases, and this is actually something you can do at home. You can find various vinegars and Drano and ammonia in your house and classify them as acids or bases. Even milk is slightly acidic, and so you could have some fun with that if you want. And we're going to a new booklet here. This was picked up by all of you before you left the school in March. And if you don't have this booklet, go on the website and download it, and then you'll have it. So I'm going to scroll down here. I was playing around a minute before I went on here. There's a webcam feature where you could see me in the bottom right hand corner, but like really, like who wants to look at me here? I'll just draw a little picture of what I would look like if you saw me in the corner of the screen. But I'm not DiCaprio, so I don't really think that would help. But it is a feature. Sometimes you see it. I know with those Tyler DeWitt videos that you can watch, including this chapter, I believe, on the website, right? The vids in the various units, he has a picture of himself. Okay. Good for him. So let's do some brainstorming here. So I'm just going to pretend that you're shouting out various answers to me. So some common examples of some acids. Kyra said HCl. Good work, Kyra. And Madison said HNO3. That's right. Let's get some guys from Chemistry 40SH. There, Ron said hydrobromic acid. And Josiah said hydroiodic acid, and just say your own name and draw in some quietly to yourself if you want, okay? So these are some common examples of some acids. Acetic acid's another one. And sulfuric acid, right? We find that in car batteries, and you can add to the list as you see fit. Then we have some common examples of some bases. Well, we can have sodium hydroxide, which is lye, and that's used in some toilet cleaner, mixed in with aluminum hydroxide, AlOH3. Remember, if you're buying toilet cleaner, look at the ingredients, and if it's $1 cheaper from the Life brand or the no-name brand, and it's the same percentages and the same ingredients, then the dollar more you're paying for is just the label, right? If you like the Drano label or the Liquid Plumber, then go ahead. But if it's the same active ingredient, get the generic, right? Okay, so those are bases. Ammonia itself is a base. Magnesium hydroxide is a base. That's called milk of magnesia. That is an antacid if you have too much pizza and beer when you're watching The Masked Singer or Tiger King. Trying to stay relevant. Common properties. What are some common properties of acids? They are corrosive, right? They'll eat away at metals. And so when you're storing an acid, you got to store it in a proper glass or treated plastic bottle. Glass is very commonly used. Other properties, well, if you taste an acid, they taste sour. Okay, don't taste acids unless you know exactly what you're tasting. Oranges have citric acid in them, as do lemons, and so they are sour tasting. Other properties of acids is that when active metals are dumped in acids, you release hydrogen gas. Not all metals, but active metals. When we talk about electrochemistry a little later in the course, we will see that. Common properties of bases. Bases are caustic. That means they eat away at tissue. So if you're dealing with lye or ammonia when you're cleaning, you should wear gloves so you don't eat away at your tissue. Bases are bitter. Tylenol is an example of a base. It's an amide, and I sometimes have problems swallowing pills, so I chew them. Some of you may be like that, and when you chew them, you get that bitter taste in your mouth. So that's an example of some common properties of bases. If it's a solid, bases feel slippery to the touch. And you can add in more properties as you go through. You know that acids are going to neutralize bases, and bases are going to neutralize acids. Okay. When we're watching this lecture, when you're watching it in the day, if you want, you can type in for fun in EDSB some more examples of properties of acids and bases. I should say lots of acids are associated with an H plus and lots of bases are associated with an OH minus, but we're going to get to that in more detail. H plus is the hydrogen ion. You could, if it's aqueous, then you can write it as the H3O plus, which is the hydronium ion, and OH minus is the hydroxide ion. Okay. Indicators. Indicators are involved with acids and bases. Litmus paper is a common indicator. It tells you when you've reached the end point of a titration. Titrations is a topic we look at lots in this chapter. It also indicates right away whether you have an acid or a base. So if I have red litmus paper and I dip it in acid, it stays red, but blue litmus paper becomes red. So blue switches to red. In a base, blue dipped in the water might look a little darker blue because it's wet, but red litmus paper dipped into a base becomes blue. So red becomes blue. Okay. Phenolphthalein, which in the old days was used in X-Lax. X-Lax is a laxative, but most of you don't give a crap about that. Phenolphthalein turned out to be a carcinogen, so they don't use it in the X-Lax anymore. Phenolphthalein is clear in an acid, but when you put drops of it in a base, it is pink. And there are some indicator titration simulations in the PHET website and other websites. You can see the color changes happening. And there are other indicators. Some are mixes of all sorts of chemicals and have a wide range of color changes depending on the pH of the solution, including something called universal indicator. Some of you may have used indicators if you've done any maintenance on swimming pools. Maybe you work at or volunteer at Parks and Rec in the summer and are involved with maintaining a swimming pool or a wading pool or something like that. Okay, so let's get a bit descriptive here on page 2 and talk about various classifications of acids and bases. There's not just one definition of an acid. It depends on all sorts of things. Because there's so many different properties, so we have different categories. Just like each and every one of you can be categorized certain ways. And I can say, okay, Jimmy, I don't think we have a Jimmy in class, but if we do, we could say, okay, let's all categorize Jimmy, but only positive things, right? So Jimmy is a son, and perhaps he has a sibling, so Jimmy is a brother. And Jimmy is a volunteer at Winnipeg Harvest, and Jimmy is the captain of the Tiddlywink team, whatever, right? You can be categorized lots of ways. That's actually a fun party game to play, but always keep it positive, right? We can do the same thing with acids and bases. So Svante Arrhenius, the Swedish guy, did some stuff with chemical kinetics, but also with acids and bases. So by definition, an Arrhenius acid, Arrhenius, is a substance which breaks apart in water and releases a H plus ion. So an example is hydrogen chloride gas. You dissolve that in water and you get H plus aqueous plus Cl minus aqueous. So HCl is an example of an Arrhenius acid. NaOH is an example of an Arrhenius base. So when you break the sodium hydroxide down in water, it breaks into Na plus and OH minus. So an Arrhenius base releases hydroxide into solution. So here we see some examples of Arrhenius acids or bases. So HBr breaks down to H plus and Br minus. So it's an Arrhenius acid. LaOH breaks down, that's lithium hydroxide, into La plus and OH minus. So that is categorized as an Arrhenius base. And H2SO4 gives you 2 moles of H plus and the sulfate. So you're releasing H plus. So that's all that's needed to call it an Arrhenius acid. Arrhenius acids and bases are used when we get into neutralization equations, but they're not the most common category that we deal with in the course. More common is this next one here, which is the Bronsted-Lowry or BL acid and base system. Bronsted and Lowry were these people from the United Kingdom who they didn't work together actually. They were actually competitors, but some people think Bronsted actually, it should just be called a Bronsted acid, and that Lowry came a little bit later on. But most people say, oh, it's around the same time. So we'll classify a substance that can donate a proton to another substance as a Bronsted-Lowry acid. And I'm going to take this part out. I disagree with this part, so I'm just going to take that out there. So a Bronsted-Lowry acid donates a proton. What does it donate a proton to? It donates a proton to a Bronsted-Lowry base. So a Bronsted-Lowry base or a BL base accepts a proton from a Bronsted-Lowry acid. So if you're talking about baseball, you can think of the hardball has the proton, the acid is the pitcher, and the base is the bat catcher, or just the catcher. Okay? So here we have an example. This is acetic acid, CH3COH. We've mentioned that before, I believe. And so it can lose a proton to H2O. So H2O acts as a Bronsted-Lowry base. It accepts the proton from the acetic acid. Okay, so H2O is a Bronsted-Lowry base, and the CH3COH is a Bronsted-Lowry acid. Now if I go back the other way, H3O plus can give a proton to CH3COH. So H3O plus is an acid, and the CH3CO minus, the acetate anion, is a base. A quicker way to write that, which I like to write as a quick way, HAC plus H2O goes to H3O plus AC minus. So the acetic acid is written as HAC, where the AC stands for acetate. It's nothing about actinium. We don't do anything with actinium in the course, so don't worry about that. Let's see. So we have this proton transfer. So let's look at these two examples here. Here we have ammonia plus H2O goes to NH4 plus and OH minus. So NH3 is a base, Bronsted-Lowry base, because it accepts a proton from H2O, and NH4 plus is an acid. It donates a proton to OH minus, which is a base. Okay, so you have this system here. Now HCl plus H2O. Now somebody's saying, oh no, you said HCl was an Arrhenius acid. Well, I also said Jimmy was a volunteer and he was also a son. So you could be categorized more than one way. So HCl, yeah, it's an Arrhenius acid, but it's also a Bronsted-Lowry acid. So it transfers a proton to H2O. So I get H3O plus Cl minus. Okay. So while I have these here, let me introduce the concept you see creeping down here of conjugate acid-base pairs. Conjugate acid-base pairs are going to, just move my microphone a bit here, differ by just one proton. And when you have two reactants on the left and two products on the right, you can have two conjugate acid-base pairs. So NH3, watch this, I'm going to use a different color, how about this? NH3 and NH4 plus count as one conjugate acid-base pair, and H2O and OH minus count as the other. And typically when you're writing you put the acid first in a pair. So NH4 plus and NH3 is one conjugate acid base pair, and H2O and OH minus is the other conjugate acid base pair. So we have the acid, and then we have the conjugate base. The difference is exactly one H plus. If I add an H plus to a base, I get the acid. So add an H plus to NH3, I get ammonium. Add an H plus to OH minus, I get H2O. Here in the second one, okay, so one is going to be HCl and Cl minus. I like to draw these little guidelines in here, and the other is H2O and H3O plus. So put the acid first, then the base in what I call the slash notation. So the conjugate base of HCl is Cl minus. The conjugate base of H3O plus is H2O. And some of you are looking, you're saying, H2O can act as an acid or as a base, and that's true. And there are a fair number of chemicals can do that, and it all depends on who they're hanging around with, who they're reacting with. Just like if you're in a group of some friends, you may act one way, and then if you're in a group with some other friends, you may end up acting another way. Let's make sure you're in the group with the friends, not the group with the other friends, right? All right. Okay, so let's look at this definition here of conjugate acids and bases. When a base accepts a proton, it becomes an acid because it now has a proton that it can donate. And when an acid donates a proton, it becomes a base because it now has room to accept a proton. These are what we call conjugate pairs of acids and bases. So, for example, HF and F minus are a conjugate acid-base pair. H3O plus and H2O, as we just saw, are a conjugate acid-base pair. And let's identify the conjugate acid-base pairs in the equation below. And if you want, I'll pause. You click on the pause button on the YouTube, fill them all out, and then press resume. Do, 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 do. And we're back. Okay, let's see how well you did. So in the first one, you got H2SO4 and HSO4 minus. That's one conjugate acid-base pair. And the other one would be H3O plus and H2O. Did you get that right? I hope you got that right. Safe? Safe, did you get that right? I hope so. Ashley, hope you got that one right. Okay, now we got HCl plus OH minus. You don't always have to have the water explicitly written on the left-hand side or the right-hand side. In the second one, we don't have it on the left-hand side. But HCl does toss a proton over to the hydroxide. So we're left with the conjugate base of HCl is Cl minus, and you got OH minus and H2O. But typically, you write the acid first and then the conjugate base. So you got H2O and OH minus is our other conjugate acid-base pair. Here in the third one, we don't see water anywhere. We see HCl tossing a proton to NH3 to get NH4 plus and Cl minus. So I got HCl and Cl minus, and I got NH4 plus and NH3. Okay, so those are my two conjugate acid-base pairs. And the fourth one we've already looked at before, H2O and OH minus, and NH4 plus and NH3. Okay, so you have to be able to identify acids and their conjugate base pairs. Some books, by the way, they'll do this. They'll have like acid 1, base 1. And then they might change the color on you. Base 2, acid 2. And then they'll draw the guidelines. You think I can stay color coordinated? If you do, you are mistaken. Okay. So more practice. What are the conjugate bases of these acids that are written here? Okay, you can pause the YouTube, try it. Do, 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 do. And we're back. Okay, so HNO3, nitric acid, the conjugate base is NO3 minus. H2O, the conjugate base is OH minus. H3O plus, the conjugate base is H2O. H2SO4, the conjugate base is HSO4 minus. Now this is a tricky one because some students say, oh, it should be SO4 2 minus. No, SO4 2 minus would be 2 protons being transferred. If I had HSO4 minus and wanted the conjugate base, it would be SO4 2-. If I want the conjugate acid of HSO4-, then it's H2SO4. Then I try to trick kids and I say, okay, I got SO4 2-. What's its conjugate base? There is none. There's no conjugate base of SO4 2- because there's no H plus to be given away. Okay, back to here. HBr, the conjugate base is Br-. HCO3-, the conjugate base is CO3 2-. So you not only get rid of the H symbol, you get rid of a plus sign, so you got one less plus sign, which means one more negative sign. So it's CO3 2-. Let me throw in some more on the side here. H3PO4 is phosphoric acid. The conjugate base is H2PO4-, and H2PO4-, the conjugate base is HPO4 2-, and HPO4 2-, the conjugate base is PO4 3-. Okay, so that one had lots going on, didn't it? Because it was triproduct. There were 3 protons that could be lost. Okay, now we have here, what are the conjugate acids of these bases? Well, I have a base with OH-, so the conjugate acid, I'm going to add a H plus to that, and I get H2O. These are the easier ones, right? It's always easier to add something than to take something away, right? H2O, I add an H plus to that, and I get H3O plus. HCO3-, I add an H plus to that, I get H2CO3. SO4 2-, I add an H plus to that, I get HSO4-. ClO4-, I add an H plus to that, I get HClO4. Questions? I hope not. Some students want to know, why do we even care about all this? It's going to help us when we deal with neutralization. It's also going to help you in your future chemistry courses when you look at buffer solutions and how buffer solutions work, because the conjugate base acid pair is important in that concept. Okay, so so far a summary: Arrhenius acids are substances that dissociate to produce H+. Bases give OH-. Acids are substances that, again, I don't like that. There's issues with that. So let's just say that acids are proton donors and bases are proton acceptors. Well, there's other ways to categorize acids and bases. So let's look at some of these other categories. We have here binary acids. Binary, when you think of a binary number system, just 2, or binary star system, just 2. So only 2 different kinds of atoms. HCl there, it can be categorized even this way as a binary acid. Just 2 kinds of atoms. HI2, HBr2, HF2, H2S. There's 3 atoms there, hydrosulfuric acid, but only 2 different kinds of atoms. So H2S can be defined as a binary acid. A ternary acid, which isn't written here, I'm going to write it here. Ternary acid would be 3 different kinds. And many oxyacids, what I'm looking at right here, are ternary. So an oxyacid, also called an oxyacid, is 3 or more different types of atoms with oxygen surrounding the other nonmetal, and hydrogens bonded to the oxygen, but not to the central atom. So sulfuric acid is a class C oxyacid. So you got sulfur in the middle. I didn't put in the Lewis diagrams, my lone pairs. There, I can put them in if it'll make you happy. So there you go. So oxygens do their best to surround the sulfur, and then hydrogens dangle from the oxygens. That is an example of an oxyacid. Very important industrial chemicals, oxyacids. There's maybe 24 very commonly used oxyacids. Nitric acid is another one, and you can draw the Lewis diagram if you want. You got nitrogen surrounded as much as possible by 3 oxygens, and then a hydrogen dangling to any one of those oxygens, and you adjust the Lewis diagram accordingly. Phosphoric acid, the oxygens surround the phosphorus, and hydrogens dangle to the oxygens. Carbonic acid, which is what happens when carbon dioxide is dissolved in water, right? When you look at rainwater, and I'm looking at some right now, the pH is less than 7, which means rainwater is acidic. And one reason why it's acidic naturally is that there's carbon dioxide in the atmosphere. So the carbon dioxide dissolves in the water to some extent, creating carbonic acid, making a pH of less than 7. Another reason why rainwater is acidic is there's other pollutants like sulfur trioxide and nitrogen dioxide, things like this from the exhaust of our factories, our cars, and that gives us acid rain with a pH could be even like 3 or less in a really extreme industrial place. So carbonic acid is an interesting chemical. And perchloric acid, that salts of perchloric acid were used as the silos for the boosters in rocket ships. So that's some pretty powerful stuff. It's an oxyacid, so you have oxygen surrounding the chlorine and then hydrogen dangling from the oxygen. Okay? So what other ways can we classify acids? We can talk about organic acid. Organic acid means you have carbon and not just carbon, but what's called the carboxylic acid group, which is the COOH group. So we have formic acid, which is HCOOH, vinegar, which we talked about before, which is a dilute solution of acetic acid. The name you might remember from grade 11 organic chemistry is called ethanoic acid. That's the IUPAC name. Acetic acid is the common name. But if you want to be part of the union, International Union of Pure and Applied Chemistry, then it's ethanoic acid. And we have examples for ethanoic acid. And then we have some other ways of writing acetic acid. Okay. What are some other? How many organic? There's lots of organic acids. There's like thousands of them, and they're important. They're important in making polymers, making textiles, clothing, biochemical processes. Lots of important reasons why we need organic acids. We can talk about monoprotic acid, means there's just one proton that can be released. Diprotic means there's two, H2S, H2SO4. Triprotic, there's 3, H3PO4, H3ASO4 is another one. Polyprotic, just in general, more than one. 4 protons, that doesn't really happen. So polyprotic means 2 or 3. Not to be confused with polypocket, which are those toy little dolls with the tiny pieces that get all over the rug and then hurt your feet. Okay. So, wow, there's lots of categories for acids and bases. We can talk about strong acids. There's only 6 strong acids. A strong acid is something that will be a strong electrolyte, make lots of ions, ionize essentially 100%. So here we have some examples. Perchloric, hydrochloric, hydrobromic, hydroiodic, nitric, and sulfuric. Well, actually only the first ionization energy. So that is a strong acid. That's all it is. HI, hydroiodic acid, goes to H plus I minus, and you don't really have an equilibrium going back the other way. It's 99%, almost 100% going to ionize to the right. There I see HClO4 goes to H plus ClO4 minus. A weak acid is just going to ionize typically less than 10%. So it wants to stay unionized. I know that looks like it says unionized, but we actually mean here unionized. It doesn't want to break up into ions very much. In 100 molecules, less than 10 typically will break up. Now HF, which you might think should be strong because the other halogens are strong acids, isn't. And that has to do with the bond energy and the distance between the hydrogen and the fluorine. So it isn't a strong acid, it's a weak acid. So the H plus isn't released so easily. And we can get quantitative about that and get what's called the Ka. Oh my goodness, an equilibrium constant, just like we looked at KSP in the previous chapter and KEQ in the chapter before that. My goodness, there is some logic to this course. How about that? So we're looking at the equilibrium constant, Ka, and it's going to be H plus times F minus over HF. We're all talking about aqueous here, so we have a denominator that's not 1, but it's the concentration of HF, and that's going to be a heck of a lot larger than H plus and F minus. So the Ka is going to be a small number. Typically, Ka's range between 10 to the minus 30 to 10 to the minus 3. Those are typical values of Ka. And here we see acetic acid, HAC goes to H plus plus AC minus, is my shorthand way to write it. And my Ka is going to be H plus times AC minus over HAC. That turns out to be 1.8 by 10 to the minus 5. I forget what HF is now. You can fill it in and send me a ESB message and give me the Ka for HF. Sounds good? I think so. Now here's something that students get confused on. The words concentrated and dilute. Those are independent of strong and weak. Here's what I mean. If I have something like hydrochloric acid, I can have 10 molar hydrochloric acid. So that's 10 moles of HCl dissolved in 1 liter. That's concentrated. That's really concentrated. You better not dip your fingers in that. If I have just, let's say, 0.0001 moles of HCl in a liter of water, it's still a strong acid. You still get the 100% ionization, but there ain't much there. So that is known as a dilute acid. So you can have a strong acid that is concentrated. You can have a strong acid that is dilute. Strong does not mean concentrated. Weak does not mean dilute. If I look at an HF solution, I can have 10 molar HF solution. Yeah, it's a weak acid, but it's still concentrated. That's going to burn your fingers big time. Or I can have a 0.0001 molar HF solution. So that's a weak acid. And that particular weak acid's concentration classifies it as dilute. So every word in acid-base chemistry matters. Don't blur them together. I see too much in everyday life where people blur the words together, and it's annoying. And it's not science. And we're teaching science here. Right? Right. There's a big smiley face. Yay, science. Okay. Here I threw in an organic acid because all organic acids are weak acids. Well, I looked at acetic acid, that's organic, but so is benzoic acid. The salt of benzoic acid, benzoate, sodium benzoate, is used in preservatives for various beverages and jams and jellies. I always forget the difference between a jam and a jelly. I'm going to say a jam is thicker than a jelly. You can ESB me the difference. So I got C6H5COH, which is benzoic acid, breaks apart to H plus and C6H5CO minus. Or if I want to just do a shorthand, I can write H-benz, where benz means the benzoate anion goes to H plus plus benz minus. So my Ka is going to be H plus times benz minus over H-benz. And then whatever that value that is, you can look it up. There's tables of Ka values, and we're going to assume in this chapter that everything's at 25 degrees Celsius unless otherwise mentioned. Okay, let's look at a little bit at strong bases. Bases don't have as many categories associated with them as acids. We have strong bases, which are the group 1A hydroxides and the group 2A hydroxides. So I list them all. Lithium hydroxide, sodium, potassium, rubidium, cesium, francium, and the group 2 hydroxide. Beryllium hydroxide we rarely deal with. So the other ones we do, and they're strong bases. So if I looked at something like magnesium hydroxide, it's going to break apart once you can dissolve it in water to Mg2 plus 2OH minus. Okay? Not all of it dissolves, but once it does, it ionizes into Mg2 plus 2OH minus. And a weak base will ionize less than 10%. And almost all the weak bases we look at will be ammonia or derivatives of ammonia, like amines, like methylamine or ethylamine. propylamine, things like that, dipropylamine. There's varieties. So the NH3 gains an H plus, NH4 plus OH minus. So that's actually a Bronsted-Lowry equation. And my Kb is my base. I don't want to call it dissociation constant because the base doesn't break apart. Rather, less than 10 of 100 are being transformed into ions, right? The NH3 is gaining a proton, so it becomes an ion, NH4 plus, and then you're left with an OH minus because the H2O now has lost its proton. You know, there are these two sodium atoms that walked out of a bar, one said to the other, gee, I think I lost an electron. The other said, are you sure? And the first one said, yeah, I'm positive. So here we got Kb, that's the base ionization constant. You can insert a laugh track if you want. And the Kb is NH4 plus times OH minus over NH3. And by a coincidence, to 1 decimal place, the Kb for ammonia is the same as the Ka for acetic acid, 1.8 by 10 to the minus 5. Again, we don't use units for that. Okay? So, let's continue a little and look at the magical business about water, because water can do all sorts of things. Water can break apart on its own to form H plus and OH minus. Okay? There's not much that does it, but in a 1 liter solution at 25 degrees Celsius, your H plus will be 10 to the minus 7 molar, and your OH minus will be 10 to the minus 7. Okay, that is just measured. Automatically that happens. It's called the auto-ionization of water, or the self-ionization. Sometimes it's called the self-dissociation, or the auto-dissociation of water. So the water breaks apart into H plus and OH minus. And my KEQ for the expression is equal to KW. So it's called the water ionization constant, and it is always 10 to the minus 14 at 25 degrees Celsius. And it is the product of H plus times OH minus. You don't divide by H2O, right? Because that's just a pure liquid. So we call KEQ the dissociation of water, and at 25 degrees Celsius, KW is 1 by 10 to the minus 14. So in pure water, the pH is neutral. pH is 7, as we're going to learn in our next lecture. So the concentration of H3O plus and OH minus are both the same, and therefore they're the square root of 10 to the minus 14, which is 10 to the minus 7. So if we have neutral water, as we just said, H plus or H3O plus, remember we're always going to assume that, I like to write H plus, it's faster, but H plus and H3O plus are synonyms for each other. That's always true. So H3O plus is the same as OH minus, then we have a pH neutral. We have an acidic solution if we dump in, let's say, some HCl, and then H3O plus is greater than OH minus, or dump in some vinegar. So we say that, another thing we can say is the concentration of H3O plus is greater than 10 to the minus 7, which means the concentration of OH minus is less than 10 to the minus 7, because their products have to always give you 10 to the minus 14. If we have a basic solution, we have less H3O plus than OH minus, like sodium hydroxide. So H3O plus is less than 10 to the minus 7, and OH minus is greater than 10 to the minus 7, the product being 10 to the minus 14. In any solution, even if you don't see it written, we're talking about aqueous solutions here, both H plus and OH minus are always present. A solution is acidic if H plus are in excess, and basic if OH minus are in excess. So we can look at some examples involving KW. Okay, so let's say we have, let's go straight to the example here, 0.1 molar NaOH. What's the concentration of everything? Okay, so it's 0.1 molar NaOH, so that means OH minus is 0.1 molar because NaOH breaks apart 100%. And then my H plus is going to be KW over OH minus, So 1 by 10 to the minus 14 divided by 0.1, which is 1 by 10 to the minus 13 molar. My pH, well, I might as well throw that in right now. pH is the -1 times the log of the H plus concentration. And log is a button on your calculator. It's a mathematical function. I can go into more details if you want. It's really 10 to what power gives you the number in the argument. So H plus, the argument is the stuff in brackets, 10 to the minus 13. So the log of 10 to the minus 13 is -13. You multiply by -1, the pH is 13. Basic solutions have pH greater than 7, as we mentioned in our properties, or should have mentioned. pOH is -1 times the log of the OH minus concentration. That P function is just -1 times the log of something. So OH minus is 0.1, so it becomes 1. And the thing we're going to learn is the pH plus, oops, let's write that again, pH plus pOH always has to equal 14. Let's look at the second example here. We're talking about Pepsi. Pepsi is 4.2 by 10 to the minus 5 molar. Is it an acid or base? Let's find out everything. Okay, so H plus is 4.2 by 10 to the minus 5. Already I know it's acidic because that's more than 1 by 10 to the minus 7. The OH minus is Kw over the H plus, so that's 1 by 10 to the minus 14. I'm doing it right now with you. 1 by 10 to the minus 14 divided by 4.2 by 10 to the minus 5. And I get 2.38 by 10 to the minus 10 molar. Okay, let's see, the pH is the negative log of 4.2 by 10 to the minus 5. 4.38. Typically pHs are given to 2 decimal places, so I'm going to do that. It's less than 7, which is good. That means it's acidic. And the pOH is the negative log of the OH minus, 2.38 by 10 to the 10 minus log minus 9.62. And lo and behold, when I add pH and pOH together, I get 14, which I have to. And that's the rule. I can prove it mathematically if you'd like. So then I see here some practice problems. Just do the odd number ones on page 8. And then I get into the pH scale. I might as well talk about it since we already have. So here I see some chemicals that are acidic, and battery acid, lemon juice, vinegar, those are all acidic. Milk slightly acidic, and then you got baking soda, milk of magnesia, ammonia, lye. Those are basic. And here we have another scale, which we've talked about before. So there you have it. Check this out. Watch for how no matter the pH, there is always some OH minus and some H3O plus. And note, pH can be less than 0. You might have done this before in junior high and got pH. Said, oh no, it can always be only be between 1 and 14. That's not true. Usually in a practical way, we don't have discussions of pH less than 0, because then you're talking about really concentrated stuff. And but you could, for example, a 10 molar HCl solution, the pH will be -1. And pHs can also be greater than 14. I see here, if you want to learn more about the pH scale, you can go to the PHET Colorado site. Here I see more about pH up close and personal with Søren Sørensen. It was a Scandinavian brewmeister. He cared about pH because he was looking at various enzymes that would work in the beer, and they only work under certain conditions, right? You may have done some biology stuff with enzymes, and some of the enzymes that break down things, if you're out of a pH range, the enzymes don't work well. So pHs are important in biochemistry. So if I take a strong acid and strong base and mix them together, I neutralize them, and we say that the pH is neutral. pH scale ranges from 0 to 14. That's not true. I just said that wasn't true. It can be less than 0 or more than 14. It's a logarithmic scale, which means you go by orders of 10. So if I had some drink with a pH of 4 and another drink with a pH of 5, then the drink with a pH of 4 would be 10 times more acidic than one with a pH of 5, and 100 times more acidic than one with a pH of 6. And this little thing I wrote in the margin here, 10 to the absolute value of the difference in pH, that's a way to say how much and calculate how much more acidic one solution is compared to the other. Same with alkaline. A pH of 10 is 10 times more acidic than a pH of 9 and 100 times more acidic than a pH of 8. Okay, this we all said before. Here's the equation. We like to use pHs. It originally came as a convenience because you don't always go 2.6 by 10 to the minus 5, right? That's a hard thing to write on a label, right? Sometimes you have these shampoos or hair conditioners which are pH balanced for long, manageable hair, right? So they want to say, or a value of 2.3 by 10 to the minus 7 for long, manageable hair or something, right? 2.3 by 10 to the minus 6, I don't know. So there's different types of problems you can have when you're determining pH. Different types of problems, type A, type B. I don't want to label them all. Let's just find some numbers here. So if an acid has an H plus concentration of 0.0001, find the pH. So the pH is minus 1 times the log of 0.0001. And I should get that to be 4, right? 0.1231 log minus is 4. And the pH is 4. The pOH is going to be 10 because pH plus pOH is always going to be 14. My H plus, if I rearrange the pH equation, H plus is 10 to the minus pH. So 10 to the minus 4, which you just got, 0.0001 molar. And my OH minus is 10 to the minus pOH. So 10 to the minus 10 molar. Okay, second one, solution has OH minus. So I just elaborated on example A. I put a few more things in there. Second one, OH minus concentration is 0.005. Find the pH. Well, let's get the pOH first. pOH is minus 1 times the log of 0.005. So 0.005 log minus 2.30. And the pH is going to be 14 minus 2.30, which is 11.70. 11.70, great. And then my OH minus concentration is 0.005. My H plus concentration, I could write it as Kw over OH minus, or I could, since I got the pH, just write it as 10 to the minus 11.70. So that's the inverse log to the base 10. 2.00 2.0 by 10 to the minus 12 molar. And always check your H plus times your OH minus has to give you 1 by 10 to the minus 14. Here I threw an example on the bottom of page 10. If pH equals 6.1, calculate H plus. So H plus is 10 to the minus 6.1. 6.1 minus inverse log 7.94 by 10 to the minus 7. Which is more than 1 by 10 to the minus 7, so this is indeed is acidic, and the pOH would be 14 minus 6.1, which is 7.9, and the OH minus will be 10 to the minus 7.9, 1.26 by 10 to the minus 8 molar. Okay, let's do another one or two. pOH, apparently the evil twin sister of pH. Fine. Okay, so OH minus 2 by 10 to the minus 9. pOH is minus 1 times the log of 2 by 10 to the minus 9. 8.70. And then the pH would be 14 minus that, which is 5.3, which makes sense. It's going to be acidic. Why? Because the H plus is 10 to the minus pH. 10 to the minus 5.3. 5.01 by 10 to the minus 6. Which is more than 10 to the minus 7. Here, pH plus pOH equals 14. We said that before. And so let's look at one more question here. Let's say H3O plus is 0.00067. Find pOH. Well, let's find everything. When in doubt, find everything. So the pH is minus 1 times the log of 0.00067, which is 3.17. And then the pOH is 14 minus that. 14 minus 3.17, 10.83. And the OH minus is 10 to the minus 10.83. 1.48 by 10 to the minus 11 molar. Okay, so we know that that's acidic because the H plus is 6.7 by 10 to the minus 4. That's more than 10 to the minus 7. Okay. Some more practice problems. Just do the odd ones on page 9 here. So here's an equation summary on page 10. pH is a convenient logarithmic scale to indicate the amount of H plus in solution. pH is negative 1 times the log of H plus, or negative 1 times the log of H3O plus, H plus and H3O plus. Two ways of saying exactly the same thing. Well, okay, fine. Not exactly the same thing, but you add H plus to H2O to get H3O plus. Hydronium ion concentration, same as H plus. As much as possible, I'm going to use H plus in these calculations. pOH is minus 1 times the log of OH minus. H plus is 10 to the minus pH. Now, if you didn't know how to do that, I got pH is minus 1 times the log of H plus. I multiply both sides by negative 1, and then take the inverse log to the base 10. So I get 10 to the minus pH. The inverse log of log is 1, so H plus is 10 to the minus pH. Consider the same story for OH minus, 10 to the minus pOH. And then pH plus pOH equals 14. And H plus times OH minus equals KW equals 1 by 10 to the minus 14. By the way, how do you get the pH plus pOH equals 14? If you want the proof, it's minus the log of H plus, which is pH, plus minus the log of OH minus equals, where you have H plus times OH minus is KW. So I'm going to take the negative log of both sides, minus the log of KW. So that becomes 14 pH plus pOH. Because when you take the log of a product, right, I'm taking the log of H plus times OH minus, that's the log of H plus the log of OH minus, equals the log of KW, multiply them all by negative 1, and I prove that pH plus pOH equals 14. In other words, it's this thing that you might have seen in math. Log of A times B is log of A plus log of B. If you don't know how to do the proof, that's fine. Just memorize the equations, use these equations. Some more practice with pH. I can do worksheet Ali Sheba. Ali Sheba was a racehorse which ran in the Triple Crown a few years ago. So you can try those questions 1 through 7. Then the next page here, you don't need to do it. It's too much, I think. If you really want, page 14. Extra review. Write all the equations we've used. Okay, there you go. And then we get to some examples of strong acid, weak acid equilibria, but I'm going to leave that for our second lecture. So there's lots of questions to do and practice, and some of these concepts are a little subtle, so practice is very important, okay, so that you'll get the basics and do well on the acid tests. Oh, you know I do those puns all the time. Okay, have fun.